I just need to make an announcement. Okay, so just a quick announcement. If your name tag has this symbol, this bottom red thing here, then you're going to the dinner this evening. So we meet at Wadham College. There's a map in the booklet and on the webpage, and it's at 6:15 drinks, somewhere called the Cloisters. I'm not actually sure where that is, but if you go to Wadham College, the porter will be able to tell you where this is. And then dinner is sharp at 7 o'clock, please. So if you want to actually come directly to the dinner, don't be later than 7 o'clock. Okay? So I hope everyone who signed up has the tag, etc. Okay, and I will now hand over to the chair.
So yeah, for the last session today, we are happy to start with Julia Plavnik, who will tell us about the homotopy coherent classification of fusion two categories. Take it away.
Thank you for the introduction, and thank you to the organizers for the invitation and for this amazing conference. So I will tell you about this joint work in progress with my collaborators, Thibaut Dicopet, Peter Houston, Theo Johnson-Frey, Dimitri Nikshik, Dave Pennis, David Reuter, and Matthew Yu. Both of the last one are here with me. And it's a fun project that hopefully will be online soon, maybe end of, or maybe some points in the fall. Not be that ambitious. So I want to tell you a little bit about the motivation of this project, so why we want to study and classify fusion two categories. So there are many things. I'm a mathematician, so I'm more inclined to the later point on this slide, but for this conference, I thought that might be nice to see that these fusion two categories are non-invertible symmetries for 2 plus 1 dimensional QFT, and we can think of them as pairs in which we have the bulk operators that come as the center of these fusion two categories. So there is a notion of center for these fusion two categories, and that are the 3 plus 1 dimensional symmetry TFT, and the boundary operators is given by this fusion two category that we are looking at. Also, we think that understanding and classifying these fusion two categories will give us hints on how to go higher even, and how to understand how to classify higher things, and revealing how intrinsically non-invertible symmetries in higher dimensions could be. And also we want to develop a framework for studying these higher objects, in particular, for example, these higher Morita categories and stuff like this. So I started studying, I'm an algebraist, so I started studying Hopf algebras, and from there I started studying fusion and modular categories, fusion one categories, and now I'm learning and studying these fusion two categories. So I wanted to tell you a little bit about the lower dimensional level before going to the classification that I want to present. So I know that there was a mention already fusion categories, even given a combinatorial flavor of a definition. So I want to give you this definition because it will be easier for me to go from this definition to the definition of fusion two categories that I want to present. So I will say that I have a fusion, that my category C is a fusion category over C if it has a lot of structures and properties. The first structure that I want to ask for is abelian C linear. So abelian means that it's a category of representations of an algebra, a finite dimensional algebra in this case, because I will ask for finiteness later. But if not, if more abstractly you want to think about it, we want to have direct sum, kernel, co-kernel for morphism. So I want to be able to do some homological algebra in my categories, basically. And C linear means that I have the home spaces in my category, the spaces of morphisms are vector spaces over the complex numbers. My category is semi-simple, so every object decomposes as a finite direct sum of simple objects. C is finite, so what I will ask is that these home spaces are finite dimensional, and moreover that I have finitely many simple objects up to isomorphisms. So I will be able to do a lot of linear algebra because of all this, so that's where the combinatorial approach also comes from. And then I have more structures, so I have this monoidal structure. I can do the tensor product of objects, and I have an associativity constraint and a distinguished object in my category that it's the unit. And there are some axioms that I'm not writing, the pentagon and the triangle axioms. My category has the property, this monoidal category has the property of being rigid. So every object in my category has left and right duals. And the last thing that I will ask, maybe I should say, this tensor product behaves well with abelian and C-linear structure also. And the last thing that I want to ask is that this simple object that comes here, the unit for the monoidal structure, behaves well with the abelian structure. It's a simple object in my abelian category. So some examples are, for example, this abelian theory. If we have a finite group and a tricocycle, we can look at G-graded finite dimensional vector spaces, and the associativity constraint, this A here, will be given by this omega, this tricocycle. We can also take twisted doubles, so we have finite group and we can find a quasi-Hopf algebra looking at this construction of the twisted double by this cocycle and look at the finite dimensional representations of it. We can also look at semi-simple Lie algebras and get some purification of some representations of them and get quantum group categories. And there is also a very nice family of categories, the Tambari-Yamagami categories, in which the input is an abelian group and some non-degenerate symmetric form. And Ising is one of the examples when A is set 2, for example. So these are some of the examples that we know. And the question that I wanted to pose here is, okay, can we describe these fusion 1 categories in terms of kind of lower dimensional data that we have in hand? With lower dimensional data, in this case, I'm meaning group data and cohomology, so groups and cohomology. And there is a nice family that can be described using that data that are called group theoretical fusion 1 categories. And these fusion 1 categories are parameterized with a group and a subgroup, a cocycle and a cochain, with some conditions. And this category is the category of bimodules over the category Beck G omega, the one that I told you, the abelian theory, for certain nice algebra in the category that it's given by H and beta. And you could go even a little further, and there is another class of categories called weakly group theoretical that maybe you could argue that are also described in terms of this group data and cohomology. It's doing some other operations, not just the group data and cohomology. You need to do extension theory and also equivariantization, taking fixed points under certain action, but maybe we could argue that. But in general, you cannot go further than that. So the answer or the slogan for this is no, groups and cohomology is not enough. For example, in the previous slide, the family of categories of quantum groups does not come from this data. And there are other exotic examples. There are exotic examples coming from subfactor theory and things like this. So groups and cohomology are not enough in this one-dimensional fusion setting. So let me say a little bit more about fusion 1 categories. In general, it's very hard to classify them. There is a lot of efforts in classifying fusion categories, and since it's super hard, because as I said, so for example, we have this example of Beck G omega or Rep G. So at least we need to understand finite groups. We need to understand the cohomology. Moreover, other example that I didn't give there, but it's Rep H for a semi-simple Hopf algebra. So we also need to understand these. And these are already hard, things that are hard to understand. And with this data, we only classify maybe in part of integral fusion categories. We are not even at the level of integral. So it's really hard. So what we have been doing, and a lot of people have been doing for a couple of years, is trying to classify a small fusion categories, braided fusion categories, or modular fusion categories. And with small, what I mean is we fix some invariant and we try to classify using some of the invariants. There are a couple of invariants. One is the rank. The rank is the number of simple objects. In my category, the Frobisher dimension is some notion of dimension that comes at the level of the fusion rules. The Galois group, we need to have a modular category, so this is for modular categories, and the Frobisher exponent is the order of the T matrix of the center of the fusion category. So there have been efforts in this, but to give you an idea on how hard the problem is, if we only want to classify fusion categories by rank, the problem is solved for rank 3 by Victor Ostrich, so only 3 simple objects. Of course, if you add more structure, for example, if we go to modular categories, there have been a lot of people working on this problem, Paul Bruglia, Richard Ng, Victor Ostrich. I have also worked on this, but Eric Rowell, Shenhan Wang, Xiao and Wen, and also Stong, that I didn't write here, but was one of the first one working on this. So the classification have moved much further. I think for now it's rank 11, and from what I was saying, rank 12 might be close to be finished. So you see, adding this modularity, which is some non-degeneracy in the braid, we can push further. But for fusion, just fusion, it's super hard. We are in rank 3. And for these other cases, I might not say much, but Galois group, we only know when it's one orbit. The Galois group has only one orbit, and we know a little bit about 2 orbits, but it gets super hard very quickly. And from each per Ron dimension, we know certain prime decomposition, or if the dimension is even or not even, but congruent to 2 mod 4, or things like this, and depends on another thing. So it's very hard. So now what we wanted to know is to see how this changed or not in the higher world, right? So now I want to introduce the main object of the talk, this fusion 2 categories that was in the title. So I want to classify, or our project today was to classify fusion 2 categories. So this definition is, definition of fusion 2 category was given by Chris Douglas and David Reuter. So, and you see it has a similar flavor to the previous one. So a fusion 2 category, C is a fusion 2 category if it has certain structures and properties. So I want to have a semi-simple 2 category. So I want to have direct sums, condensations, and the home spaces these times are categories, and I want that categories to be semi-simple. I want to have this category to be finite, so again, finitely many simple objects. I want to have a monoidal structure. Again, I want to have dual, so I have rigidity here asked. And the unit object, this is my unit for this monoidal structure. I didn't write it there, but that's the unit for this fusion 2 category. It's a simple object, okay? And this is one picture, so there is a nice graphical calculus in this word, and this is half of the 10J symbols in this category. So it's one side of the equation. And this is thanks to David that has it in his website, and I stole it. So maybe I mentioned simple objects, so let me tell you a little bit about that. So we would like to understand how are the simple objects. To do that, one thing that we can look is, we know that the home spaces in these categories, in these fusion 2 categories, are semi-simple categories. So when we look at the endomorphisms of one object, they are moreover multi-fusion 1 categories. So multi-fusion is almost the same that I said before when I said fusion. The only thing that changes is that the unit is not simple. You can decompose the unit. But the condition of simplicity, of fusion in this detects simplicity on the objects. Or you could think on the lines and that this category is fusion means, as I was saying, we already have multi-fusion, so the only extra condition is that the unit, in this case the identity map, is simple, so I want the endomorphisms of the identity to be the complex. So I will extract here a distinguished object that we will be looking at a lot in this talk. So omega of C of my fusion 2 category will be the endomorphisms of the unit. This is the distinguished monoidal unit in this fusion 2 category. And again, in principle, it's a multi-fusion 1 category, but the unit was required to be simple, so it's a fusion 1 category. And as usual, when we look at the unit, that gives me some commutativity, so I have actually a braided fusion 1 category. But a lot of things that when you are used to work in fusion 1 categories happen, in fusion 2 categories break, and one of the things that break is Schur's lemma. So when we were in fusion 1 categories, if I have 2 simple objects, and they were isomorphisms between them were isomorphisms or 0. So I have that condition. But here now, I could have non-isomorphic simple objects with non-zero morphisms between them that are not isomorphisms. So what we will look at are the connected components. So I will say that 2 simple objects are in the same connected component if there is a non-zero morphism between them. So I will consider this set of connected components of the fusion 2 category. And I want to give you some examples before going further. So one kind of the basic example that we will consider is 2vec, which is the fusion 2 category of finite semi-simple linear 1 categories. Other example that is this. And some of these examples might remind you a little bit of the examples that I said before. So here what I will have, this 2vec pi g, I have G a group and pi a cocycle here too, but I will have now two vector space or G-graded two vector spaces. And here I have this also deforming, I don't know where, like this, okay, here deforming. So here this will be like group-like things, like before I said abelian theory. So again, this will be group-like things or invertible symmetries, or we can think that these are only surfaces going on here. Whereas this other, it's the fusion two category of modules over, this will be a braided, so V here is a braided one fusion category. So I will consider the modules over this braided fusion category, and I then can consider the functors of B modules and the natural transformations or of B modules here. And this will be my fusion two categories, and this will be only lines. This is connected. So I have only one connected component in this case, and connected categories actually look like this. So this is an important example. And there are other examples like we have before, I didn't mention before, but rep G is an example of a fusion category. Here we have two rep G, or here we can, instead of taking G a finite group, we can have this with a one form, or there are a generalization, or a higher version of Tambara-Yamagami that Thibaut Dicopet and Matt Yu define in their paper, in which, so Tambara-Yamagami are very nice and have something specific about having the trivial component being one of these Beck G, and they do some generalization of this, but they need to require, instead of a group, two groups. So it's a nice generalization, and there are other examples. So now I want to pose a similar question to the one that I proposed before. Can we describe these fusion two categories now in terms of lower categorical data? And with this, I'm still using groups and cohomology, because you saw that one of my examples was this 2-vec G pi, so I need groups and cohomology. And also now I need braided one fusion categories, because I gave you this example mod V, which the input was a braided fusion one category. And I want to know if this is enough. That's the question. So similar to the other question. But in this case, the answer is positive. And for me, it was a surprise, to be honest, because I'm more familiar with the other word. And in the other word, this was not enough. So now we can, in this joint work with my collaborators, we can parameterize fusion two categories in terms of braided fusion one categories and group theoretical data. But with this, what I want to say is that if we have an oracle that tells us everything we want to know about group theory, about cohomology, about braided one fusion categories, and even the Picard group of them and how they interact, we can describe all fusion two categories. Okay? So before giving you the classification, that's the idea of what's going on, but before giving you the parameterization, I want to introduce some notation that will be useful to understand more or less the flavor of this classification. So as I was saying, we have here this important object that I mentioned before. This was the endomorphisms of one, remember? So this was a braided fusion one category, so it makes sense to look at the Muger center or symmetric center of this. This tells you how far your category is from being symmetric, okay? The category. So, and this is a symmetric category itself. So here I'm looking at this symmetric fusion one category, and by the linear theorem, we know that every symmetric fusion one category over the complex numbers, so here it's important that I'm working over the complex numbers in characteristic zero, are always of the form rep G set. I think it was already mentioned in one of the previous talks that this happens, where set is a central element in the group of order at most 2. And here what I'm doing are like super representations if I'm in the super case, right? So this set, it's messing around with the braid when it's not 1, and when it's 1, it's just rep G. So we will actually distinguish these two cases. So my fusion 2 category will be called bosonic if this Muger center is Tanakian. Tanakian means that set is equal to 1, and I have just usual representation, finite dimensional representations of a group, of a finite group. And it will be fermionic if this is the super case. So if my symmetric category coming from the Muger center of C is super Tanakian, so it will look as super representations of the supergroup G set. Now, one comment that I wanted to make is that for me this is very natural because that's how we understand some things in Fusion 1 categories, but it's also very interesting and it's also kind of easy to compute, to be honest. That's why I also like it. But maybe from a theoretical point of view, it's also interesting to know that this condition that here we are looking in the Muger center and these transparent objects can be read from the loops of the center of the Fusion 2 category. So this, the Fusion 2 category being bosonic or fermionic will depend on how these loops of the center of my Fusion 2 categories are. If they are Tanakian, it will be bosonic, and if they are super Tanakian, this will be fermionic. So this if and only if saying here that basically the emergent particles depend only on the bulk theory, maybe for physics, and for math that it's kind of a Morita invariant what's going on here. Okay. So now I can give you the classification. So this is the first bit of the classification. We have these two cases, so Fusion 2 categories are bosonic or fermionic, so I will divide it in those two cases. I will present the bosonic because I think it's more transparent how the data is appearing. So bosonic Fusion 2 categories are parameterized by a non-degenerate braided Fusion 1 category. So non-degenerate is like modular, but forgetting the ribbon structure. So it's that this Muger center that I was saying before is Beck. The only transparent object is the vacuum, the unit. So the input will be one non-degenerate braided Fusion category, an inclusion of finite groups. I will have H and G, and I will have this inclusion. I will have a categorical action from H to braided tensor autoequivalence of A. And here, I want to say that I'm thinking of these as two groupoids. It's a higher, it's not just a group homomorphisms. I need to be one level high, okay? And then I will have a class in this cohomology, in the H Harper 4 of this group G, with coefficients in the units of C, and some homotopy between the anomaly of this action and the pi restricted to H. So let me tell you how some of the data comes through, at least some of it. So remember that these loops of C are braided Fusion 1 category. So again, I can look at my Muger center, that's a symmetric Fusion 1 category, and by the linear theorem, since I'm assuming bosonic, this needs to be rep H for a group, and not a super case, I mean the group case. So here I'm already recovering H somehow, or at least I have the H from there. And then what is important is that since I have a Tanakian Muger center, there is a construction that let me kill it, so I can kind of, I don't know if this is exactly the right word for physics, but I can condense that and I will get a non-degenerate category. So I will get one without transparent objects. So I will be in the non-degenerate world, and there is a process to go back that it takes fixed point under the action of H. So here I will recover my loops doing the equivalentization of this non-degenerate category A with certain action by H. So I have here this correspondence between the loops and these three pieces of data. And the other part is that between these two things that I was mentioning before, the loops of the center of the Fusion 2 category and the Muger center of the loops of the Fusion 2 category, there is a dominant braided functor, and that induces this, I mean, because of the symmetric bosonic case, since I'm assuming that this is bosonic or Tanakian, this is also Tanakian because of the dominance, as I was saying in the previous slide. So I have I have this dominant braided functor between this rep G and rep H for some G and my original H from before, from above, and now that gives me an inclusion between H and G. The other piece of data, the cohomological data, I don't want to. Yes, Shawan?
I want to understand what is the object in this Fusion 2 category? What their fusion of, are they related? So they have described just an object. In the fusion kind of have an object, have a one morphism, etc. But what is the fusion of the object?
The fusion of the object. But here I'm looking. So for now, I'm at this level, that I'm looking at the endomorphisms of the unit. So from the endomorphisms of the unit, I can already recover this part. The thing is that later, when I have this thing here, I will be able to take the equivalentization, but this rep G, and I will have some G cross and some other things will come up. I don't know if Matt or David have a better answer, but from this part, I'm looking at this.
Sorry, I have a question on the equivalentization. So is it the equivalentization of the H crossed extension of A, or is it just gauging the H action on A? Do I have to do a H crossed extension?
This will be a braided fusion 1 category, the result.
Oh, so yeah, so there is
with rep H inside.
Okay. So it's okay.
Yeah. So now I want to give some examples to understand a little bit the data. Okay, and I will be fast so I can get to the end. So if I give you that H is equal to G, then I start with a non-degenerate braided fusion category, that's input. This is something that I'm giving to you. And now the action, instead of being from H to A, it will be from G. So I will have this categorical action now. And remember, the loops will be now the equivalentizations of A by G. And this class, the pi will be determined by the homotopy. So my category will be of this form, one of the connected categories that I mentioned before. And there are other examples. The first one is the same that I just said. So it's just a connected category, a connected bosonic fusion two categories. We recover in this case. Now, if H is trivial instead, I will recover these decoupled things because the data of H and G will not mix at all. So I will have one of these only lines and one of the only surfaces, and I will decouple. And when A is back, what happens is that I have this condition, the loops of C are rep H, and this is equivalent to say that the category is group theoretical, which is also defined by T1 Matt in their paper with the Tambari-Yamagami, and it's a category, a higher version of the one that I mentioned before, the group theoretical. So let me tell you in 1 minute the fermionic classification. All the orange is the things that I changed from bosonic to fermionic. So if I start with a fermionic fusion two category, it's not surprising that now I will not have any longer a non-degenerate, I will have a slightly degenerate. So it's a super modular category without the ribbon structure. So the symmetric center is super Beck instead of Beck in this case. Now I will have supergroups here and an inclusion of supergroups. This condition is a little bit more complicated and I will not spell out everything, but the idea is that instead of having just a categorical action as before, now I have to have some super higher group in mind and a super cohomology. And then the homotopy between the super anomaly and this restriction of the super cohomology. This is much more tricky and technical than the previous one. And for example, a Lagrangian algebra approach, maybe it's useful for the other case, but for this one, it's different. And just, I will mention in 1 second or in 0 seconds that we have a lot of nice profit. There is an Ognanu rigidity result for fusion two categories, meaning that there are no non-trivial deformations for fusion two categories, rank finiteness, so there are only finitely many fusion two categories up to a given rank, and I define there what it's a rank, but it's related to the number of connected components and the rank of the loops, and that there are some double coset, that is what David mentioned before. So thank you.
I just wanted to make a comment that we had a paper yesterday where we have the bosonic classification as well. We use some physics arguments by stacking some TQFTs and gauging some diagonal groups to obtain the same classification.
Okay, that's great. I will take a look. Thank you.
But we don't have the fermionic one yet, so yeah.
Thanks. Thank you.
So these two groups, G and H, are they related to the universal grading of the fusion category?
These two groups are related to the universal grading.
Easy guess would be every fusion two category is always a representation category, the module category of a fusion category. That's not too far from that.
I don't know if it's a universal grading. I don't think so. I don't see how. We didn't even define this.
The universal grading is somehow the pi zero, and this is like this double coset.
The universal gradient is related to the double coset.
Yeah.
Do you think that for 2n categories, a similar classification will persist? I mean, it's obviously not true for the odd ones. I think.
I'm not sure. I don't have that much intuition in higher, to be honest. This was already surprising for me. I don't know, David, if you have. For me, it was surprising that was only the.
Okay. You think so? Okay. So in the 2n ones will always be group-like in order that somehow.
This twisted cohomology would be more and more complicated. Like this thing that replaces supervectors. Why I can also take
just two more questions.
I want to know to what extent are your parameterization injective? I mean, it seems like you have given a map from some data onto the or fusion two categories, and hopefully it's surjective. I want to know, is it if and only if, or you have some redundancy?
So we have some data that I didn't present here, but we parameterize this with certain squares, and I put all the data in this list, but there are some squares, and we have some equivalence to go from and back.
Yeah, because this is related to the one-dimensional lower case where you actually don't use a subgroup, you only use it up to conjugacy. And here you have more delicate data, you have some group cohomology as well, so maybe you only have some
there are things that are not unique. For example, I don't know if this one, but sometimes some decompositions that you can do for fusion two categories in terms of something invertible and something like this are not always unique. But we do have this equivalence between the data. We have functors going both ways.
Last question, quickly.
I wonder in this fusion 2 category, whether the fusion of the object is always pointed, and that's gave rise to one of your group, H or G. I wonder whether there's such understanding.
I would say no. I don't think it's always pointed.
Okay.
Thank you. Let's thank the speaker again.